framework right here. And we'll do this one in Matlab. So let's go to Matlab and let's try to make some order here and this. So here we're going to have a new section. We're going to call it problem 1 part C, and we're going to clear all old variables. Clear all. And we're going to define the coefficient matrix, which, if you remember, is 1, -1, 2, first row, -1, 1, 0 for the second row, and -1, 0, 1 for the third row. I'm going to put a semicolon because I don't want it to output. And now what I want to do is I want to check for repeated eigenvalues, because it becomes a weird thing when I use the Jordan with repeated eigenvalues. So I just use the eigenfunction, and I see I don't have repeated eigenvalues, but I have these things right here. So now I need to have a lot of visualization to do this completely in Matlab. So what do we want to do? Well, the first thing that we want to do is we want to plug each of these back in. So let's say we have the first lambda for L equals 1. So for L equals 1, I'm going to have this right here, but I'm going to subtract 1 to the diagonal. So second row is the second column, third row is the third column. And then I'm going to augment this with zeros, and I'm going to RREF it. So I'm going to reduced row echelon form this to find my value. Then I'm going to do the same thing for lambda equals to 1 plus I. So now I'm going to RREF that same matrix A, but now I'm going to subtract minus 1 plus I plus square root of -1, and I'm going to subtract this to the diagonals, so here and here, and then I'm going to augment everything with a 0. Now that I did that, I'm going to have RREF of this as well, and we'll see what we get out of this. So we get here, this right here, which tells us that we can basically determine one of the vectors. It says that the first one has to be 0, but the second one, let's see, this tells us that let's say that this is x, y, and z. So x has to be 0. So defining the eigenvectors, what are we going to have? Well, K1 is going to be equal to, the first one has to be 0, because this is x equals 0. The second one and the third one are dependent. So if y is equal to 2z, so if z is equal to 1, then y is equal to 2. So this is our first eigenvector. Then how do we deal with this other answer? This is a complex answer. But first of all, we'd like to see the whole matrix, right? So the whole matrix tells us, let's do it like this. Awesome. So the first matrix tells us that we can decide the third row, that here we have x, so let's kind of write it down. Here we have y, and here minus z, that's equal to 0. And then here we have that x plus iz is equal to 0. So here we can rewrite this as y is equal to z, and here we can rewrite this as x is equal to negative iz. So if z is equal to 1, then we're going to have x is equal to negative I, which is negative square root of negative 1. Then y is equal to z, which we said is 1. And z is equal to 1. So this is our second vector, our k2. Now why is this useful? Well, because we can use this, we can look at the real part and the imaginary part. This is the imaginary part, and these are the real parts. So we can rewrite this as, the real part is going to be 0, 1, 1, and the imaginary part is going to be negative 1, 0, and 0, all multiplied by that I, which is the square root, so I'll just write I, because we're not going to execute this. So this is negative I, negative I. So you see where I'm going? If I add these up, we get this again, but this is the real part, and this is the imaginary part. So I can write that my first solution is going to be with this eigenvector, so it's going to be k1 times, so let me just use this one, times e to the whatever the value was that it came from. And we know that the eigenvalue came from lambda equals 1. So 1 to the e to the 1t. And that's one answer. Now another answer is going to be the real part of this, which is this one, times the cosine of the coefficient of the I. Well, we have that I has a coefficient of 1. We're not looking at the signs. So coefficient of the I times t minus the imaginary part, which is this one, without looking at the I, just the coefficient of the I, times the sine of t again, because it would be the coefficient of I. Now, this is also to the, so everything has to be multiplied by e to the 1t, so just t. And this comes from a theorem that I explained in playlist 10.4. And this is going to be one of our solutions. Now the other solution is going to look similar to this, so I'm going to copy and paste it and change some things. So this is going to be x3. It's still going to be this, but now we're going to have this here, and the real part is going to go here, and this is going to be a plus. Now we want to check each solution individually so that you can see if you got a mistake for each one individually. So let's say that the derivative of x1 has to be equal to a times x1, and all of the other ones 2. So x2 has to be equal to x2, and x3 has to be equal to x3. And let's see what we get. Oh, this now we can comment it out because that wasn't part of the code. It was just part of the reasoning. And now it's telling us, hey, we don't know what the variable t is. So I'm going to declare the variables sims, and I'll use C1 and C2 and C3 later. So I'll just put them in now. And now we get this, and we did everything correctly because we're getting the same thing on the left and on the right for all of 3. So now I'm going to define the general solution. This would be the complementary solution if there was a forcing function, but there isn't one. So our general solution, x of t, I'll write it capital X of t, is going to be c1 times x1 plus c2 times x2 plus c3 times x3. And then we have it over here. I don't know if you can see that. There it is. And now we'll just check this one too, checking the general solution. So we'll do the same as before. We'll say the derivative of that general solution has to be equal to a times that general solution. Press Control Enter, and we find that it is indeed. So this is how you would do it completely in Matlab. I hope this was helpful, and I'll see you next time.